Hello everybody, and welcome to our video on improper integrals. Okay, so far all of the integrals we've dealt with have been on finite intervals and have been functions that are continuous on those intervals, or at least only had maybe a hole in the graph, but no asymptotes for sure. So now we're going to talk about the situations where we want to integrate over an infinite interval, or integrate over somewhere where there's an asymptotic discontinuity. So the first example we're going to look at is the function f of x equals 1 over x squared. And so we've got the graph here, so from 0 to infinity, and we're looking at the area under the curve from 1 onward. So we're looking at all of this area, and we never want to stop computing the area. I want to see how much area is under that curve. And a lot of times the initial reaction, or the initial thought, is to think, well, it must have infinite area, because you're going to take this area under the curve forever. But that's actually not necessarily the case. So let's go ahead and, just as a little example here, try to set up the integral for this thing. And what do we get? So we're going to let our area function be the integral from 1 to t of 1 over x squared dx. So right now what I'm doing is just computing the integral from here to here, where t is just some stopping point on the graph. And what do I get? I get negative 1 over x, evaluated from 1 to t. And then we plug in and we get 1 minus 1 over t. So when I plug in the t, I get a negative 1 over t, and then a minus the negative 1. And so then we get a positive 1. And notice that that means that the area, no matter what I pick for t, the area is always less than 1. No matter how big I move t out, t could be 10,000, it's always going to be less than 1, because it's 1 minus some fraction. And also notice that when I take the limit as t goes to infinity, the area approaches 1. Okay, so let's actually properly define this thing. The definition of an improper integral of type 1 is that if the integral from a to t of f of x dx exists for every number t greater than or equal to a, then the integral from a to infinity of f of x dx means the limit as t goes to infinity of the integral from a to t of f of x dx, provided this limit exists. In other words, the limit is finite. So what we're saying is, when I write the integral from a to infinity, what I mean is take the limit as t goes to infinity of the integral from a to t. This is just a shorthand. Now, a lot of times what I'll see students do is plug in infinity, treating it like a number. But this really doesn't work. Once you start trying to treat infinity like a number and plug it into functions, you'll start reaching logical contradictions. So we don't want to create that bad habit. We want to remember that, hey, when I write this integral, I always need to turn it into a limit and use the limit to compute the value. Okay, so that's A. Now let's take a look at B. If the integral from t to b of f of x dx exists for every t less than or equal to b, then when I write the integral from negative infinity to b of f of x dx, what I mean is the limit as t goes to negative infinity of the integral from t to b of f of x dx, provided this limit exists, that is, it is finite. So if we look at this first case up here, this is describing I have some starting point A, and my function goes off to the right, and I'm looking for all of the area to the right. And this second case, B, says I have some upper bound B, and a function going off to the left, and I'm looking for all of the area going to the left. Now we say the proper integrals from a to infinity of f of x dx and negative infinity to b of f of x are called convergent if the corresponding limit exists, and divergent if the limit doesn't exist. So convergent improper integrals means the associated limit exists. Divergent improper integrals means the limit doesn't exist. Now, if both the integral from a to infinity of f of x dx and the integral from negative infinity to a of f of x dx are convergent, then we define the integral from negative infinity to infinity of f of x dx as the sum of the integrals from negative infinity to a of f of x dx and from a to infinity of f of x dx. So in other words, if I want the entire integral from negative infinity to infinity, then I have to pick a breaking point, let's say here, and split that integral up into two. If you don't do this action of splitting an integral up into two when you're doing negative infinity to infinity bounds, you can actually end up in a case where if you try to set up the wrong type of limit, like if you tried to make this negative t to t, you can compute something where it looks like that limit actually exists, but it doesn't really. So we need to split these up, because if the limit from a to infinity doesn't exist, then right there we're done. If either the limit from negative infinity to a or a to infinity doesn't exist, we can just stop. It's not convergent. Okay, so let's do an example. Determine whether the integral is convergent or divergent. So here we've got the integral from 1 to infinity of 1 over x dx. The first step in all of these problems is going to be to rewrite this in the form of a limit. So the limit from 1 to t, the integral from 1 to t as t goes to infinity of 1 over x dx. And now I can integrate what's inside the limit normally. And the integral of 1 over x is ln of the absolute value of x. Now I need to evaluate it from 1 to t. And so this becomes the limit as t goes to infinity of ln of the absolute value of t minus ln of 1. And ln of 1 is 0. So this is just the limit as t goes to infinity of ln of the absolute value of t. And we know that when t goes to infinity, the natural log function also approaches infinity. So this is infinity. In other words, the integral, so this implies that the integral from 1 to infinity of 1 over x dx diverges. Anytime we don't get a finite number, we say that that integral diverges. Doesn't matter if it's infinity, negative infinity, or we just get some oscillating values, we still say this improper integral diverges. All right, next, we've got the integral from negative infinity to 0 of z e to the 2z dz. Well, as always, the first thing I want students to do is rewrite this in limit form. So we'll call this the limit as t goes to negative infinity of the integral from t to 0 of z e to the 2z dz. Now, this is an integration by parts, a pretty standard integration by parts integral. So I'm going to let u be z and du be dz then. And I'm going to set dv to e to the 2z dz, which when I take that antiderivative will give me e to the 2z over 2. And now I can set up my integral by parts inside the limit. And I get u v minus the integral of v du, which is e to the 2z dz over 2, evaluated from t to 0. So this gives me the limit as t goes to infinity of z e to the 2z over 2 minus e to the 2z over 4, evaluated from t to 0. And here I'm going to factor out, we'll factor out e to the 2z over 2. Well, actually, I'm going to plug in first, and then we'll do our factoring. So we'll plug in our values for 0. I get 0 times e to the 2z minus e to the 0 over 4, which is 1/4, minus, plug in t, we get t e to the 2t over 2 minus e to the 2t over 4. And now we'll do a little bit of simplification. So I distribute this negative, and since this term becomes positive, I'll now write that first. E to the 2t over 4 minus t e to the 2t over 2. Okay, so it's not super clear whether this integral exists or not yet. So we've got to see if we can make that work. I did just notice a little typo. These should have been negative infinities, and for some reason in that second step I started writing positive infinity. I've always got to make at least one silly typo in any video. Guaranteed. Okay, so what's the problem with this negative infinity? Well, if this is going to negative infinity, I have this product here, t times e to the 2t. E to the 2t is going to go to 0 because its input is going to infinity. So you may recall the graph for e to the x looks like this. So if x is going to infinity, if the input is going to infinity, then the output is also going to infinity. And if the input is going to negative infinity, the output approaches 0. So e to the 2t here, since t is going to negative infinity, this expression goes to 0, but t goes to negative infinity. So we get infinity times 0. That's an indeterminate form. So we've got to rewrite this limit a bit. And what we're going to do is two things. One, we're going to split the limit on the sum. Write this as the limit as t goes to negative infinity of negative 1/4 plus the limit as t goes to negative infinity of the remaining expression. But I'm also going to factor out e to the 2t over 2 here. Gives me 1/2 minus t left inside. Now I've made a little bit of an assumption here. By splitting up this limit, I'm assuming that both of these limits exist. I'm going to show that they both exist now. This first one exists obviously because it's just the limit of a constant. The second one, we're going to have to apply L'Hopital's rule to. Now if I found that this limit didn't exist, I'd have to go back to the drawing board and go back here to this step and try something else. But it's going to work out, so we'll be all right. Okay, so now I'm going to off to the side deal with this limit separately. So the limit as t goes to negative infinity of this expression, but I'm going to write e to the 2t in the denominator, so I'll get it as e to the negative 2t. And then up top we still have 1/2 minus t. Now, since I already have a negative in this expression, my e to the negative 2t, when t goes to negative infinity, my exponent is becoming large and positive, so this thing goes to infinity, and this 1/2 minus t also goes to infinity. So this has infinity over infinity in determinate form. Which means we can apply L'Hopital's rule. And so we take the derivative of the numerator, which is -1, divided by the derivative of the denominator, which would be 2 times -2 e to the negative 2t. We just had to apply the chain rule there. And now, e to the negative 2t is still going to infinity. And when we have a fraction whose numerator is a constant, but the denominator goes to infinity, or negative infinity for that matter, the whole fraction goes to 0. So the limit of -1/4 is just -1/4, plus the limit of this expression is going to be 0. So altogether, this is -1/4. Okay. And sometimes you'll get negative values for these limits. You might be a little tripped up by that, but keep in mind, from negative infinity to 0, the value of z is negative here, so we'd expect our integral answer to be negative if the limit exists, which it does. Okay, so moving on. Example 3, the integral from negative infinity to infinity of 1 over 1 plus x squared dx. So we've got our integral from negative infinity to infinity. So that tells us first we have to split this integral into 2. And you can pick anywhere to split these integrals up that you want, as long as the function is defined at the point and all that. But you usually want to just pick a number that makes things easy. And in this case, z is easy, because the antiderivative of 1 over 1 plus x squared is arctangent of x, and arctangent of 0 is one of the few values that people may have memorized for that function. So this becomes the integral from negative infinity to 0 of 1 over 1 plus x squared, plus the integral from 0 to infinity of 1 over 1 plus x squared. And now we'll convert both of these into limits. So I'll use t for my limit variable in the first integral. So this is negative t, or let's make that t going to negative infinity, and t in the denominator, or not the denominator, the lower bound, I should say, to 0, 1 over 1 plus x squared dx, plus the limit as, let's call this n. N goes to infinity, of the integral from 0 to n of 1 over 1 plus x squared dx. Now we evaluate each of these antiderivatives. So this becomes the limit as t goes to negative infinity of, and the antiderivative for 1 over 1 plus x squared is arctangent of x. So I'm going to skip a little step and go straight to the evaluation. Arctangent of 0 minus arctangent of t. And I'm running out of room, so we're going to go ahead and move this to the next line. So that's the first integral evaluated, plus the limit as n goes to infinity of arctangent of n minus arctangent of 0. Now, arctangent of 0 is 0. And we know that because tangent of 0 is 0. So if I invert the input and output, we get the same thing. Arctan of 0 is 0. Now, as for the limits, as t goes to negative infinity and positive infinity, and n goes to positive infinity, for that, we have to know the graph of arctangent. And so let's just take a look here real quick in case anybody's a little rusty. If we look at the graph for tangent of x just on a single period, so just from negative pi over 2 to positive pi over 2, then the graph for arctangent is what you get when you switch the x and y values. And that's the same thing as reflecting over the line y equals x. So if you try to picture this curve flipping over the line y equals x, you should get a graph that looks like this. Now, since before we had vertical asymptotes at x equals pi over 2, now we'll have horizontal asymptotes at x equals pi over 2 and negative pi over 2. Right? So your x values become y values, and likewise your horizontal and vertical asymptotes switch when you take the inverse of a function. And so now looking at that picture, I can say, okay, well, that tells me that when when my input is approaching infinity, the output is approaching pi over 2. And if the input is approaching negative infinity, the output approaches negative pi over 2. It's a little sloppy. I'll rewrite that a bit. Okay. So arctangent of t here is approaching negative pi over 2, but the whole thing is already negative, so a negative of a negative gives us positive pi over 2 plus. And then we look at arctangent of n as n goes to infinity. That goes to positive pi over 2. So this is pi over 2 plus pi over 2, which is pi. And so the integral converges. In general, I do want students to make a habit of writing that every time, even though I think in the last example, I didn't specify that. I should have. Okay, moving on. So now we're moving on to type 2, the discontinuous integrands. So what that means is we're dealing with an integral that has a discontinuity somewhere in a finite interval. So for the integral from a to b of f of x dx, consider the case that f has a vertical asymptote in the interval from a to b. So here we've got a vertical asymptote at b. So we have to look at what happens when we take an integral from a to t and t approaches b, since the function would be undefined there. And if I have the integral from a to b and the asymptote is at a, then I need to take t approaching a from the right side. So in this first integral, t approached b from the left. Here, t approaches a from the right. But if I had an asymptote in the middle, I would need to split my integral into two. And I'd need to have one t value approaching c, and then maybe the other one would be n and approach c from the right. Okay, so let's formally define this thing. If f is continuous on the closed interval closed at a, open at b, and discontinuous at b, then the integral from a to b of f of x dx is defined as the limit as t goes to b from the left of the integral from a to t of f of x dx. So again, I'll draw this picture one more time. My integral is from a to b, but there's some kind of asymptote here, and so I take some t and I move it towards b, and that t is approaching b from the left. And that really matters because when you do these integrals of these discontinuous functions, the direction that you pick for t could change the value of the final integral. So whenever you're not totally sure, you can always draw your interval and plot a t somewhere in that interval and ask yourself, does t have to move to the right or the left to approach the asymptote? So it's moving to the right, but that means we read this as t is approaching b from the left. Similarly, if f is continuous on the interval from a to b, including b but not including a, so it's discontinuous at a, then the integral from a to b of f of x dx is defined as the limit when t approaches a from the right of the integral from t to b of f of x dx. So similarly, so we'll draw this picture again, a to b. You've got an asymptote at a. So you're looking at some function like, oh, I don't know, should I be approaching from the left or right? Put a t in your interval and ask yourself, where's the discontinuity? Oh, at a, I've got to go that way. So I'm approaching a from the right. The improper integrals from a to b of f of x dx are called convergent. That should say r, but r. Called convergent if the corresponding limits exist. Wow, that sentence was a mess. Or maybe I should have just said, here we go. The improper integral, a to b, of f of x, is called convergent if the corresponding limit exists, and divergent if the limit does not exist. All right. Now finally, if f has a discontinuity at c, where c is in the interval from a to b, then the integral from a to c of f of x dx and c to b of f of x dx are both convergent. Then we define the integral from a to b of f of x dx as the integral from a to c plus the integral from c to b. Now, these definitions apply also when the discontinuity is removable, like a hole, but usually in that case we would remove the discontinuity, so we'd find a continuous function, maybe by simplifying. So for example, if I had x squared minus x over x, and I was integrating, say, from 0 to 1, we could take a limit here, but we can also remove the whole by factoring out the x. Now, although these functions won't be identical, they will have identical integrals, so I can cancel the x over x and evaluate this way. So in the case of a whole, rather than an asymptote, we usually would just remove the discontinuity by canceling some factor or simplifying in some way, and then evaluate the integral in our standard ways. But if we have an asymptote, then those discontinuities aren't removable, so we don't have that option. Okay, so let's take a look at this example. Evaluate the integral from 2 to 3 of 1 over the square root of 3 minus x dx. Now first I have to figure out, where do I have a discontinuity? And we always check the standard kinds of places. Where would we be dividing by 0? And let's see, natural logs, for example, have asymptotes at 0 as well. So we can't divide by 0. We can't have a natural log of 0. We have to check if we have trigonometric functions, what the domain of those functions are, just all the normal stuff. In this case, it's pretty obvious that we have a discontinuity here where 3 minus x can't be 0, so x can't be 3. So I need to figure out, okay, how do I set up my integral? I look at the interval from 2 to 3 and I go, okay, the discontinuity is over here at 3. So I put some t down here. T has to go towards 3. So t is approaching 3 from the left. So we set up our limit as the limit when t approaches 3 from the left of the integral from 2 to t. And I'm going to change this notation. Instead of 1 over the square root of 3 minus x, I'm going to move that straight to 3 minus x to the negative 1/2 power. Now I do need to do a little substitution here. U equals 3 minus x. So du is negative 1 dx. Or in other words, dx is negative du. And so this becomes the limit as t goes to 3 from the left of, all right, well, we do need to change our bounds. U evaluated at 2 is just 1, and U evaluated at t is 3 minus t. Or, yes, there we go, t. So this becomes the integral from 1 to 3 minus t of u to the negative 1/2 power and a negative du. But I'll put the negative in front of the integral. Now, one thing I'll do here real quick is note that since I have a negative in front of the integral, I can always switch the bounds of the integral. And it doesn't make a huge difference, but it can make the algebra just slightly cleaner to work with. It's not going to change much, but I'll make it now the positive integral from 3 minus t to 1 of u to the negative 1/2 du. And now I'll take my antiderivative. So that's the limit as t goes to 3 from the left of u to the positive 1/2 divided by my new power, 1/2, evaluated from 3 minus t to 1. And dividing by 1/2 is the same thing as multiplying by 2. So this becomes the square root of 1 minus the square root of 3 minus t. And so now we can see why this direction, getting this direction correct, was really important. Because if t was approaching 3 from the right, I would have 3 minus a number bigger than 3, and this square root would be undefined. So we would think that the limit doesn't exist here. But actually, since t is approaching 3 from the left, then 3 minus t is just approaching 0 normally, and the square root of 0 is 0. So altogether, this works out to be 2 times the square root of 1, which is 1. So I just get 2, and hence the integral converges. Okay, so that's it for that one. Let's move on. Okay, so example 5, evaluate the integral from 0 to 1 of 3 over x to the 5th dx. Again, I look at my denominator. That's the first place I'm going to look the vast majority of the time. And I go, well, that can't be 0, so x can't be 0. And if I draw my interval from 0 to 1, and I plot some t inside the interval, and I say, hey, where does t need to go? Where's the discontinuity? The discontinuity is 0. So t is going this way, towards 0 from the right. So I set up my limit. The limit as t goes towards 0 from the right of the integral from t to 1. And I'm going to write this as 3 times x to the negative 5th dx. And now we integrate like normally. That becomes x to the negative 4th divided by the new power, evaluated from t to 1. This is the limit as t goes to 0 from the right of negative 3/4 times 1 over x to the 4th, evaluated from t to 1. That's the limit as t goes to 0 from the right of negative 3/4 times 1 over 1, which is 1, minus 1 over x to the 4th, or t to the 4th, I should say. T to the 4th. Okay, so now when t is going to 0 from the right, we've got a fraction whose denominator is approaching 0 from positive values. So this fraction approaches positive infinity. But I've got a negative out in front, so this whole factor approaches negative infinity, and then I'm multiplying by a negative again, so the whole limit approaches positive infinity. So we say the integral diverges. All right, moving on. So now we're going to talk about a very important theorem, and this theorem in particular is going to come into play when dealing with series, which will happen later in the class. So this theorem is called the comparison theorem, and it says something that's actually fairly simple. It says, suppose that f and g are continuous functions, with f of x being greater than or equal to g of x, which is positive for all x greater than or equal to a. Then if the integral from a to b of f of x dx is convergent, then the integral from a to infinity of g of x dx is convergent. And if the integral from a to infinity of g of x dx is divergent, then the integral from a to infinity of f of x dx is divergent. In other words, look at this graph here. I'm saying if the area under f is finite, then this smaller function g, the area under it has to be finite as well. And on the other hand, I'm saying if the area under g is infinite, then the area under f must also be infinite because it's got more, right? And more than infinity is still infinity. So that's all this is saying. If I've got a finite area under f, then the area under g, which is smaller, is also finite, and vice versa. If the area under g is infinite, the area under f, which is bigger, would be infinite. Now, I've written this comparison theorem as a to infinity, but of course, the same theorem could be rewritten with b, let's say, negative infinity to b for our integral. You would just swap out that expression. I just wasn't going to write the comparison theorem 3-4 different ways. You can do it with negative infinity to b. That's totally fine. You can also use the comparison theorem on negative infinity to infinity integrals. You can also do it on integrals from a to b, where f has an asymptote. On the interval from a to b. So any of those cases, all of the cases for these improper integrals that we've considered would also work perfectly fine with the comparison theorem. You would just swap out all of the integral formulas in here, the integral expressions, with the appropriate expression to restate it in terms of those other integral types. But again, same exact statement otherwise. Okay, so let's do an example. Use the comparison test to determine whether the integral is convergent or divergent. So here we've got the integral from 1 to infinity of x plus 1 over the square root of x to the 4th minus x dx. Now, one of the big mistakes I see students make is trying to just jump straight to, okay, I should know what the function is to compare it to immediately, and then validate the comparison. But that doesn't really work out. You have to actually discover what function to compare it to. So what I mean here is, I don't know what the second function is. I don't know if this function is f or g in my graph. So if I say, is this f or g? I don't know. I don't know if it's going to be the function that's smaller than another function to compare to, or bigger than another function to compare to. And you shouldn't make any assumptions about that. Instead, what you want to do is try to discover a function that is easy to compare to it, and just see if it works out. If it doesn't, you try again. So, what do I mean? Well, let's look at just the function itself, x plus 1 over the square root of x to the 4th minus x. So, what changes could I make to this function that would make it bigger or smaller? What do I mean? Well, if I look at this x plus 1, when I make a numerator larger, then the whole fraction gets bigger. So if I remove the 1, I'm making the numerator smaller. So if I just compared this to x over the square root of x to the fourth minus x, my numerator is smaller, and so the whole thing is smaller. X over the square root of x to the fourth minus x is smaller than x plus 1 over the square root of x to the fourth minus x. And what's my goal here? My goal is to find a function that's easy to integrate. I can't integrate this. If I could integrate it, I just would. I wouldn't bother with the comparison test. Now, I want to find a function that I can compare this thing to, but I'm not forcing it. I'm just saying, hey, what do I know? I know if I got rid of this 1, I'd have a somewhat simpler function. And also, this function is going to be smaller than the original one. Now here, I'm subtracting x from x to the fourth in the denominator. So as long as x is positive, which it is, keep in mind, x is positive because the integral bounds are from 1 to infinity. If I'm subtracting a positive number from the denominator, then my denominator is getting smaller, right? So in other words, if I remove that, so I have x over the square root of x to the fourth, that means this denominator is bigger, but a bigger denominator is a smaller number. And x over the square root of x to the fourth is x over x squared. Again, x is positive, which is 1 over x. So again, I didn't try to assume what the function is, and I didn't assume whether this function, the original function, was the bigger function or the smaller one. I'd made no assumptions either way. So what did I discover? Hey, this is bigger than 1 over x, so I'm really thinking of this in the formula above as the f function. That graph is not the actual graph of the function we're dealing with here, just for visual idea. So I know that I should compare it to 1 over x, and so what I'm going to do is look at the integral from 1 to infinity of 1 over x. And we've already done this integral. It's the limit as t goes to infinity of the natural log of the absolute value of x evaluated from 1 to t. I'm skipping some steps because we did that earlier. But I would expect generally, you probably most of the time have to redo the integral because you probably won't know how to do, you won't already have a result for that. Just wanted to make this one a little quicker. Now we know that this gives us the limit as t goes to infinity of ln of the absolute value of t, and we know that that is infinite. So the integral from 1 to infinity of 1 over x dx diverges, which implies, so again, this integral diverges, and the function 1 over x is smaller than the one we were dealing with, so this bigger function also diverges when we integrate it on the same bounds. So that integral diverges, and we should always cite our theorem by the comparison test. So this is a little bit tricky at first, but it's a really important skill set, especially for later on in the course dealing with series. And it's something that if you practice it, you do 3, 4, 5 problems on your own. Once you get used to working through the thought process, it becomes pretty natural after that. That being said, I'm going to go ahead and tackle a rather challenging version of this problem. So a comparison test problem where I have an integral that's much harder to work with. But actually before that, I guess I should go back. I want to make one little comment because we often ask, okay, well, why is the comparison test useful? Why does it help to tell whether these things are divergent or convergent? And it comes down to using approximation techniques. So if I know that an integral is divergent, I know that I can't compute a value for it, period. So I'm done. I don't have to waste any time. determining that one of these improper integrals is convergent by using the comparison test may not allow me to compute the actual value, but it tells me that I could possibly get good approximations using approximation techniques. So this is sort of like dotting our I's and crossing our T's before wasting time trying to approximate one of these functions. If you can determine, hey, this thing converges, so hey, if I need to know this value, it's worth trying to do a approximation technique. And if we can't confirm that it converges, if instead we show that it diverges, then we know, hey, this thing isn't going to have a value, so there's no point in trying to compute it. And as I've mentioned before in a previous video, at least I think I did, we will deal with approximation techniques later on in the course. Okay, so on to this next example. Use the comparison test to determine whether the integral is convergent or divergent. And here we have two problems. Well, we will have two problems. Let's hold up. I'm getting ahead of myself. So first, I want to try to find a function to compare it to. So I look at x over x cubed plus 1, and I never try to force the comparison. I just go, what could I change to make this expression simpler? Well, if I got rid of this 1, it would be a much simpler function, x over x cubed. But a bigger denominator is a smaller number. So that should look like that. This x over x cubed plus 1 is less than x over x cubed, which is 1 over x squared. So my temptation is to look at the integral from 0 to infinity of 1 over x squared dx. But now we have a problem. And what's that problem? The problem is that there's a discontinuity at x equals 0 and an infinite limit. So the way you would normally deal with this is you would split this thing into two. Maybe I'd separate it from 0 to 1 of 1 over x squared dx plus the integral from 1 to infinity of 1 over x squared dx. But then I end up with something very contradictory, which is that this thing, and I'm going to have to show this rigorously. I'm just kind of showing you the thought process ahead of time. I would find that this integral converges, but this one diverges. And so I would say that the whole integral from 0 to infinity diverges, but that doesn't help me and doesn't match up with this inequality I found. And the problem is, this function, the original function, does not have a discontinuity at x equals 0. It has one at x equals negative 1, but that doesn't matter because it's not in the bounds of our integral. So this causes us some issues. So how do we deal with this? Well, this was just some thought process before we actually dig into the problem. What we're going to do instead is first manipulate the original integral. So we had the integral from 0 to infinity of x over x cubed plus 1 dx. And I'm going to split this into two. The integral from 0 to 1 and the integral from 1 to infinity. Now, this function is continuous on the interval from 0 to 1, so the fundamental theorem of calculus guarantees it is a finite integral. All continuous functions intervaled on or integrated on closed intervals have finite integrals. That's part of the fundamental theorem of calculus, right? So we've got that the one portion of the integral is finite, and now we'll do the comparison with the second portion of the integral. So now the comparison that I figured out, the 1 over x squared, is perfectly fine because I only need to actually do the comparison from 1 to infinity. So I look at my integral from 1 to infinity of 1 over x squared dx. That's the limit as t goes to infinity of the integral from 1 to t of x to the negative second dx. That's the limit as t goes to infinity of x to the negative first power divided by negative 1, evaluated from 1 to t. I'm going a little quickly on this, but it's a pretty standard integral. So this is negative, we've already got the negative in the denominator, so negative 1 over t minus a negative, which becomes positive 1 over 1. And the negative 1 over t, when t goes to infinity, this fraction goes to 0. So the whole thing is 1. And since 1 is finite, so since the integral from 1 to infinity of 1 over x squared dx converges, that implies the integral from 1 to infinity of x over x cubed plus 1 dx converges by comparison. And finally, that implies that the integral from 0 to infinity of x over x cubed plus 1 dx converges. Right? Because this integral from 0 to infinity is now the sum of two finite integrals. Right? The integral from 0 to 1 and the integral from 1 to infinity. All right. So that's it. That is, I think, literally the hardest possible version of one of these comparison theorem problems, for sure. Okay. Now, our last question. And this question can kind of be thought of as a theorem. So we can kind of call this a theorem. What values of p is the integral convergent? For which is it divergent? With the integral from 1 to infinity of 1 over x to the p dx. And this is very valuable to know because it tells you a lot of these comparisons. Notice this integral here, we used 1 to infinity of 1 over x squared dx. That's the same thing as this when p is 2. And if we look at the example before, the function we compared to was just 1 over x, which is the same as this integral when p is 1. So knowing a few general facts like this about certain types of integrals can make finding comparisons easier, and that's why we're taking a look at this. So we have to break this up into cases. The first case we're going to consider is p equals 1. And the reason we have to break that case out is because we know that when p is anything other than 1 here, we would use our power rule for antiderivatives. But when p is 1, this is the function 1 over x, and that antiderivative is ln of the absolute value of x. So we have to treat that case separately. So I'm going to call this star here, my integral, because I don't want to have to rewrite it for every case individually. So star becomes the limit as t goes to infinity of the integral from 1 to t of 1 over x dx. And since we've already looked at this one twice at this point, I'm going to skip straight through all the simplification. We get the limit as t goes to infinity of ln of the absolute value of t, and that's infinity. So that implies that the integral diverges for p equals 1. Okay, so now we'll look at both case 2 and 3, and we're going to split those up after we do a little bit of work first. So here, p is not 1. So when I rewrite my integral, becomes the limit as t goes to infinity of the integral from 1 to t, and we're going to write it as x to the negative p power. Now I take my antiderivative, I add 1 to the power, so negative p plus 1, but I can also write that as 1 minus p over the new power, 1 minus p, and I evaluate from 1 to t. That gives me t to the 1 minus p over 1 minus p minus 1 over 1 minus p. And now, here's where we have to split up into case 2 and 3 separately. So now I'm going to call this double star, just so I don't have to rewrite it every time. So now we get into case 2 specifically. And case 2, we've got to consider p is not equal to 1. It could be greater than 1 or smaller than 1. And we're going to start with p being greater than 1. Then this second integral becomes the limit as t goes to infinity of t to the 1. Well, I guess I have to rewrite the integral anyways, so a lot of good that does me. 1 minus p over 1 minus p minus 1 over 1 minus p. Okay, well, the point here is that if p is bigger than 1, then 1 minus p is negative. So 1 minus p is actually approaching, or is negative, I should say. So less than 0. So t to the 1 minus p is approaching 0. Right? So you can think about it like this. Like if I have t to the first power, that's going to infinity. T to the negative first power is 1 over t, so that goes to 0. All right? Same thing applies for any numbers written in that form. If my exponent t is to a negative power, then I make it a reciprocal, and the term goes to 0. So since 1 minus p is negative, that means this whole thing approaches 0. And what I get is negative 1 over 1 minus p, which is the same thing as 1 over p minus 1. And so that implies that the integral converges. Now for case 3, that's when p is less than 1. And if p is less than 1, that means 1 minus p is positive. And if p is positive, then this whole expression, or if 1 minus p is positive, this whole expression goes to infinity, and that implies that the integral diverges. So what did we figure out? We figured out that when p was 1, the integral diverges, and when p is less than 1, it diverges. So in summary, we say the integral diverges for p less than or equal to 1, and converges for p greater than 1. All right, well, that's it for that one. Thank you for watching.